Let's get this show on the road. Okay, so I'm going to mute you all, so please answer. It makes me feel like I'm not alone when I ask questions. We're going to be looking at the dot product. And essentially what the dot product allows us to do, at least this version of it, it allows us to find the angle between any two given vectors, like these two here. The cool thing is that the vectors can be, and very often are, in 3D, right? So they're sticking out of the screen like this. So just for completeness sake, I'm going to pick a couple of questions. One where we're finding a missing angle, and one where we're actually going to use a version of this formula to get the value of a dot product. And once we've done that, we'll then move on to section 2, the second thing of today. We're going to test whether two vectors are orthogonal, parallel, or just neither. Some questions like that. And then, we'll talk about 3 when we get to it. So imagine I have a vector, and it's 1, 0, 3. And I have a second vector, and it's -2, -2, 1. And I would like to imagine this is the vector in 3D. There's U. There's V. Oh, someone brought this up, so I might as well do it right now. Have some of you do that funny little hat above your vector? Have any of you seen that notation?
I haven't.
Right. You know that is totally fine. If you want to write it that way, you go ahead. There's no right or wrong notation, right? There's lots of notation that are all right, but just in case, you know, you're used to one notation, I don't want you to get confused and change it. So anyway, I'd like to know the angle between these two vectors. In other words, I'd like to know theta, and that's pretty straightforward. And so cosine of theta is the dot product. So what's that? 1 times -2 plus 0 times -2 plus 3 times 1. And the magnitude of u, which is that fella, which would be what, the square root of 1 plus 9, so it's the square root of 10. And that's 4, 4 and 1, which is square root of 9. I know that's 3, but I'm just going to leave it as 9. And that's -2, nothing, and 3. So we end up with what? I guess 1 over the square root of 90. And to get theta then, it's the inverse cosine. Well, I'm going to change that a little bit. There, make it look pretty. So the angle between these two vectors is that. And I've noticed that some of the homework questions want 2 answers. That's the exact answer. That's what you physically write down in the first version, right? And then they want the answer, let's say, to 2 decimal places. So you got your calculator, you do an inverse cosine, and you do whatever this is, 1 divided by 3 times square root of 10. Hopefully I put enough brackets in, and I got 83.9 degrees. 83.95 degrees if it was to 2 decimal places. And so that, let me see if I can tell you what the exact words are. One's that exact, and the second one, they call it approximate. Obviously, you're rounding off, that's why it's approximate. And I did it to 2 decimal places. Now that I've looked, at least the question I'm on wants it to the nearest whole number, in which case it's 84 degrees, you're right. You know how WebAssign sometimes is okay and sometimes it's not? So if I typed that in, it might have made it, it might have said I was wrong because it wanted this. Sometimes it's okay, but you know, you're never sure about WebAssign how generous it's going to be with your answers. Are we comfortable about that pretty standard question? Here are 2 vectors, tell me the angle between them. Are we good with that question?
You got the absolute value again.
Say again?
Can you go over how you got the absolute value of the vectors?
Oh, when you see that symbol there that looks like the absolute value, that's actually the magnitude of the vector. I know it's the same symbol,
Oh, okay.
Right. And you get it by basically taking 1 squared plus nothing squared plus 3 squared, and that gets you 10.
Okay.
So the magnitude of any vector is the square root of the sum of the squares of its components. So that would be -2 squared plus -2 squared plus 1, which adds up to 9, square root of 9. We good?
Gotcha. That makes sense. Yeah, thank you.
Yeah. And let's move on to our next group of questions. And the next group of questions are, you're going to be given 2 vectors and you're going to be given a choice. And the vectors are going to be orthogonal, which means that the 2 vectors are at right angles to each other, right? That's orthogonal. They're going to be parallel, which means they kind of look like that. Or they're going to be neither, which means really anything at all can happen, right? And we can do this test by using this fella. Let's look at what makes 2 vectors orthogonal, right? If you get an angle of 90 degrees, that means the 2 vectors are orthogonal. So couldn't you just do the calculation and say, oh, it's 90 degrees? You can also get it, oops, I'll call them U and V, if the dot product is 0. Because if you put 0 here, won't you get the cosine of theta is 0 over, don't care, because 0 over a number is still 0. And what angle has a cosine of 0? 90 degrees, right? So this is equivalent to that. Now, if you want them to be parallel, the angle is actually one of 2 possibilities. If 2 vectors are parallel, then the angle between those 2 vectors would be what number? So if this was my one vector and this was my other vector, and they're parallel, right? If you put one on top of the other, what would the angle between them be?
0.
Yeah, agreed. But there is a second, less obvious possibility. Do you know parallel could also be, imagine the tip of my pen is indicating direction, right? Going this way and the other one's going that way. If you put them together, do you see that they, yeah. So all you need to do is find the angle between the 2 vectors using our friend over here. And if the answer to the cosine is 1 or -1, so if you get to the point where cosine theta is plus or -1, one of them means 0 and the other means 180, but don't you have everything you need to prove they're parallel, right? That's what parallel looks like. And the easy one is neither or neither. And that is, if it ain't 90, and if it ain't 0, and if it ain't 180, it's something else. And if it's something else, it counts as neither. Does that make sense? So if I gave you 2 vectors, for instance, if I gave you these 2 guys here, remember these 2? When you go through the whole process, won't that count as a neither? Because the angle's 84. If this was 90 degrees, you'd say orthogonal. If this was 180 degrees, you'd say parallel. Or if it was 0, you'd say parallel as well. Are we good with that? Do you want to see an example of that, or just talking it through is enough?
You could provide an example. I'm still cloudy about it.
Okay. I like people to tell me things like that. Okay, so here is an example of that in practice. Question, I think, I'll tell you the numbers that do these questions. Question 11 does it. Question 12 does it. Question 13 does it. Okay, so there's your 3 questions that do them. And there's quite a few examples in each. So let me pick, let's pick 13 then, because that's one I'm on. The 2 vectors are -3, 4, -5. And the other vector is 4, 4, -1. So the cosine of theta will be the dot product divided by the magnitude of the first one times the magnitude of the second one. Okay. Dot product, -3 times 4. Add 4 times 4. Add -5 times -1. All over. You're just going to trust me on that. The answer's 13. And the answer on this one is the square root of 33. You want to check it later, but that's the answers, right? No, it's not. I told you a pork pie. It's the square root of 50. I thought that was going to be 3, 5, 12, but whatever. So let's check. Yeah, it is. So trust me now, it is square root of 50. Right, if I put the whole package together, -12, add 16 gets me 4, 4 add 5 gets me 9, so I guess it becomes this guy here. Since I'm only interested in the angle, I don't need to worry about, you know, tidying these up because they're going to go straight into a calculator anyway. And I'm pretty sure I don't need to go anywhere, but that's going to be a neither. But let's double check it. Cosine of 9 divided by bracket square root of 50 times square root of 33. And the answer I get is the nearest whole number, 77 degrees. So that is a neither. Can we pretend in a different question that I ended up with cosine of theta ended up being eventually 1? Right, that could happen. Then when I do the inverse cosine to find out what angle that's true for, the inverse cosine of 1 is 0. Do you see that would count as a parallel? Let's pretend I got -1. Well, the inverse cosine, oops, let's close that out of the way. The inverse cosine of -1 gets me 180. That would count as parallel. And the last possibility is couldn't I end up with cosine of equals 0 if I do an inverse cosine of that guy? Although I'm pretty sure I would have guessed it was 90 long before that, because for that to happen, won't the dot product already have to be 0? In which case, when that happened, I would stop looking. I'd say, right, I know the answer. It's orthogonal. Are we good with it? Now, most questions are 3-dimensional vectors, but you can actually do it with 2-dimensional vectors as well. And can you do a dot product with only 2 numbers? And you can get a magnitude. That's what the square root of 2 squared plus 4 squared. And this one's what the square root of 1 squared plus 5 squared. So you can do it with 2. And theoretically, although they don't give you one, couldn't you do it with 10-dimensional vectors? I have no idea. I don't think anyone in the universe has any idea what the angle between 2-dimensional vectors is. But can't we still calculate it even if we don't know how to visualize it?
Yes,
and
sir.
I think, oh, cool. And as the last kind of little hiccup, you know, I don't like this notation, but other people do, and that's fine if you're one of the people who like that. Couldn't the vector u be written like that instead of as a component? It doesn't change a darn thing, it's just the way they write it.
It's crazy how I had to come all the way here just to learn that notation with the greater and less than symbols. Because my whole life I was taught with the I, J, and K.
Oh, I don't know if that's better or worse. Knowing these little brackets, they're basically brackets that look like greater than or less than. Are these brackets helpful, harmful? Don't really care.
They save time.
Save time. Yeah, I like them because You know, when it's minus 3i plus k, I always get the wrong one as a 0, right? If they miss out one of the terms. It's so easy to do. That's because I'm careless. So here is a connected to that question, right? Finding angles between things. But this time we are going to be given the coordinates of 3 points. And I'm actually going to do a question that involves them. I'll try to find one. Question 10 is an example of this. Let's have A, 1, 2, 3. B is 4, 1, 0. And C is -1, -1, 2. And making no attempt to be realistic, but there is a theory that says, as long as the 3 points are distinct, right? They're not on top of each other or on the same straight line. Won't 3 points make a triangle in 3D space, right? Here, you know, here, 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 right? So we want to know 2 things. First thing we want to know is the size of all 3 angles, right? Angle A, angle B, and angle C. And then there's a backup question to at least some of them. And that backup question, because I'm find it, yeah, is this triangle right angled or not? So the ones that have the backup are 14, I think 15 as well. No, 15. Yes. So 14 and 15 are also about a triangle in 3 points. But in these last 2, they ask you, is it right angled or not right angled? So I'm going to do it with this. Right, I need a strategy, don't we? We need some way of finding angle A. Let's focus on that. So how do you think I'm going to go about finding the size of angle A?
Do the dot product for A and B.
Okay. Now, if you want to get the vector from A to B, I don't normally write this down, but I think it's worth it for this one time. Right. Why do I not bother with that? Because I almost always do the second guy take away the first. So this is how I go. 4 take away 1. 1 take away 2. 0 take away 3. See how quick it is when you just say second take away first. Right? Second take away first. Second take away first. Second take away first. There's your vector AB. So that's that one. And now I'm going to get AC. Okay. Cover this up so it doesn't distract me. Second, take away first, -2. Second, take away first, -3. Second, take away the first, -1. Are you comfortable with the vector AC? Right? Now, isn't that like U and V, right? That's like AB and that's like AC, right? So I can use the dot product formula, which says the cosine of the angle in between is the dot product of the 2 vectors divided by, the magnitude of the vector AB times the magnitude of the vector AC. Okay, cover that up because it's distracting me. Dot product, 3 times -2 plus -1 times -3 plus -3 times -1. And that guy, all over the length of AB. Right, if you take this guy, square him, and add them up, you get 9, 9, and 1. So that's the square root of 19. If you square these guys and add them, you get 4, 9, and 1. That is the square root of 14. Are you happy about where I got these 2 magnitudes from? Right, square, square, and square, add them all up. Square, square, and square, add them all up. Because you're squaring things, aren't you always going to get positive numbers, right?
It should be square root of 19 times square root of 17 because you're missing another 4.
I am. Darn it.
Uh,
Where? This one?
Well, on the magnitude of AC.
Okay, let's check it. 4,
Oh, I
9, and 1.
forgot. Oh, forgot. Sorry. I
No,
thought
that's
I
fine.
was.
I 9 a million times. I'd rather you tell me and I was right than let it slide when I'm wrong. Because when you go and look up your notes, if I'm wrong, isn't that going to throw your brain? Like, how come that's not what I think it should be? Am I doing this wrong, kind of thing, right? So I'd rather you tell me if you think I was wrong, even if I end up being right. Very rarely I do end up being right, so that's okay. What's that? -6. Well, that's +3. Almost screwed that up. So that's -3. Oh, would you look at that? Let's check it. -6, add 3, add 3. All over the square root of 19 times the square root of 14. Wait a minute. Isn't that 0? Does it matter that I divide by ugly square roots? No. And if you're 0, doesn't that make the answer 90 degrees? Agreed? So if I draw this triangle that you can't see anymore, here's A, here's B, and here's C. Hey, orthogonal.
Whoa.
What?
No, and it just confused me how earlier 0 meant 180 and now 0 means 90.
No, 1 makes 180.
Oh, 1, it was 1. Gotcha.
1 and -1 makes 1 makes 0, and -1 makes 180. But I still got that handy, because maybe you wrote it down a little quickly and you got it back to front. Here we are. Now it's the angle, right? And you get that from the cosine being plus or minus 1, right?
You see that line above confused me where it says parallel because it's like 0, then my bad.
We good?
Yeah, you're good.
Right. This question is pretty much 90% done. Since the question was going to be, you know, what are the 3 missing angles? And then after that, it was going to be right angled. Would you agree that I can say it's going to be right angled, even although I haven't finished the question, right? So I need to find that angle there because I want to. I could have went for C, but I'm going to go for B. And now I'm going to do a deliberate mistake here. Oh, I want the angle B. So I'm going to do AB. And the other one I'm going to find is BC. If I found those 2 vectors, I would not be getting the right angle B. Look at the picture and tell me what 2 vectors should I use to get this angle at B? This will not do it.
BA and BC?
Agreed. When you want to find an angle between 2 vectors, shouldn't both vectors start with the angle that you want, in this case B? You might say, well, what am I getting here? You're actually getting an answer to a different question. If I draw, this picture's getting really messy here, but if I draw AB up here, isn't the answer I'm going to get the rest of 180? Because this is essentially the same as that guy, right? So when you center them and leave, that's the guy you've got. So just be careful that you've got all your guys in a row and that you're all pointing in the same direction. So I need a BA. And I also need to get a BC. But I can do a little bit of work or save myself a little bit of work. I've already found AB, agreed? And I could just do second takeaway first, and I know that would work and it's not a big deal to do it that way. But I can actually tell you what BA is by using these numbers. If AB is these 3 guys, who is BA?
I got you. So BA is gonna be 1 minus 4, -3, then 2 minus 1, 1, 0 minus 3, -3.
Right. Couldn't you just take AB and switch the signs and get the answer quicker?
Yeah, I guess.
Yeah, that's what I was getting at. But could you do it the way you said? Totally correct. You got it right.
Yeah.
Now, the other one I have to do from scratch. So to get BC, cover this guy up. -1 take away 4 is -5. -1 take away 1 is -2, and 2 take away 0 is 2. So there's the other vector. And so the cosine of theta is going to be the dot product of those two divided by the magnitude of those two. So -3 times -5 plus 1 times -2 plus 3 times 2. Square me, and add. So that's a square root of 19. Square me, and add. That's 4, 4, and 25. That's 8 and 25, 33. So it's positive 15. Take away 2, add 6 over these two guys. 19 over these two guys. So theta, the angle I'm interested in, is going to be the inverse cosine of that guy there. And to the nearest whole number, let's assume that's what they want. Inverse cosine of 19 divided by, oh, almost made a mistake there. Almost forgot my bracket. Then I'll do the square root of 19 times the square root of 33. When I do that, I get about 41 degrees to the nearest whole number. So we already know this guy, got him first. He was 90 degrees. We've just found B, which is this guy, which is 41 degrees. I don't need to do an awful lot of work, do I, to get this one? How will I find the third angle without going through this performance one more
The
time?
sum of a triangle is 180, so you could just subtract the two component you just found.
Agreed. Are you comfortable with that? And this triangle is right angled, which we knew way back, right? But couldn't I have, because I randomly picked it, couldn't I have found those two first and then discovered that was 90? Any questions about, here is 3 points, they make a triangle, tell me what kind of triangle, tell me the missing angles. Are you comfortable about that type of question, which boils down to these 3? You like them, guys?
I like him.
You like them. We are getting pretty close to the end here of what we need to do in this section with the dot product, and then we'll move over to another guy called the cross product, but we still have a few things to tidy up. First thing we're going to do is called direction cosines. Kind of hard to draw, but I'm going to make an attempt. There's our typical Z, right? There's our X, and there's our Y, right? So I'm trying to draw a vector that's a 3-dimensional vector, right? And can we imagine that the vector is this guy here? Right? I'm going to call the vector V because I have to call him something. Now, if you can imagine this pen is that red pen, right? Because it is a 3D thing, right? It's sticking out of the ground. This vector makes 3 different angles. They're called the direction cosines. Strange name for them until you find out how you calculate them. And then it's a kind of, okay, I can understand the name. Doesn't this vector make an angle with the x-axis? It also makes an angle with the y-axis. And lastly, doesn't it make an angle with the z-axis. Those are the 3-direction cosines. So I'm going to try my best, but this picture is going to get really messy really quickly. That angle there, the one you make with the x-axis, is called alpha. That's its name. Now, the angle that you make with the y-axis is called beta. And I've run out of color, so I guess I'll use this color. And the angle you make with the z is called gamma. Can you just about visualize what angles I'm talking about in this really messy 2D picture trying to show you 3D stuff, right? But I had a look at the textbook and their picture is just as bad as mine. So it's not, well, look at this, they're much better, right? It's just hard sometimes, isn't it, to show 3D in 2D, right? So we would like to know the size of angle alpha, beta, and gamma, the direction cosines, as they're called. And here is the formula for them. The cosine of alpha, the cosine of beta, and the cosine of gamma. Now I'm going to take the vector v and I'm going to rewrite them as v1, v2, and v3. Right. So v1 is essentially the x component of the vector, v2 is its y component, right? And v3 is its z component. This guy here is v1 divided by the magnitude of v. The cosine of b is v2 divided by the magnitude of v. And gamma is v3 divided by the magnitude of v. Can you see why the name direction cosines came about? Now, if I want to know alpha, don't I calculate this and then I do an inverse cosine, right? I calculate this and do an inverse cosine and so on. And this is just a much, I guess, prettier way of writing the formula down, right? It's a little bit prettier. So all you need is an example. So the example I'm picking is question 16, I think is one, and 17 and 18. So let's pick 16. I guess that's the one I decided on earlier. Right, so the vector v is going to be 2, 1, negative 3. Okay. I'm going to find the magnitude of v, which is 2 squared plus 1 squared plus negative 3 squared, which is what? Square root of 14. And so the cosine of angle alpha is v1, which is 2 divided by square root of 14. The cosine of beta is 1 divided by the square root of 14. And the cosine of gamma is negative 3 divided by square root of 14. So if you want to find this guy, and finally that guy, you just take the inverse cosine of that fraction, the inverse cosine of that fraction, and the inverse cosine of that fraction. And let's do it to the nearest whole number then. So inverse cosine 2 divided by square root of 14. The answer you get is about 58 degrees to the nearest whole number. This fella is inverse cosine of 1 divided by square root of 14. And the answer I get is 75 degrees. What do you think the third angle is? And you'll probably be wrong, but that's okay. How do you think I might go about finding the third one? Because math is full of structure and you might expect this structure to exist, but I'm telling you it's wrong. How might you do it?
You add up like a pattern of it.
and take it away from 180. Does that seem reasonable? Isn't it annoying when things that you should expect to happen don't always happen? So let's do it. The inverse oops, put it on first.
It's
The
not,
inverse,
not a triangle, right?
yeah, it's not a triangle, exactly. So what you get is pretty random. In this case, it's 143 degrees. You see, that's a lot bigger than 180. But you could get less than 180, right? Can you imagine if I move that, angle around a little bit, I might make it quite close to the X and Y and not too far away from the Z, and get three angles that add up to, a lot less than 180. Which means that you have to find all three of them, isn't it? There isn't a shortcut. Are we comfortable about if I give you a vector, can you find alpha, beta, and gamma, the direction cosines?
Yeah.
Yeah. So there are two more for you to try in your own time. I'm going to jump out to a new place. This is, I think it's only question one. I hope it is only question one. Yes, it is. Question one has a strange little puzzly question. There is no calculations. You're only telling me, is something meaningful? What does that mean? Right. When you do a dot product, isn't the answer a number? 42, 0, -7, right? But can't you only do dot products with other vectors? You can only do a vector 1, 2, 3, dot product 4, 5, 6. Right? It doesn't make sense to do a dot product with 5, which is just a number, right? Oh, by the way, numbers are called scalars, right? So you can't do a dot product with a scalar and a vector, right? It has to be two vectors or it don't make sense. Or as they call it, it's not meaningful, right? So could you do A dot B dot C?
Come
A
again?
dot B gets you scalar, right? And a scalar dot C is not meaningful. Because it's a dot product of a scalar and a vector. Now, when you write A dot B like this in brackets, and then outside it, you put a C, that's like saying 5C or 20C, right? Isn't that just a multiple of C? Not a dot product of C, but a multiple. So A dot B of the vector C does have a meaning because it's a scalar multiple of a vector. Scalar multiple is the fancy name for 5 times a vector, 2 times a vector, right? A number and a vector. We call them scalar products. Dot product is vector dot vector. Dot products get you scalars. Scalar products get you vectors. You see, there's a difference in the answers. What do you think C is? Meaningful or not? Could you get an answer? It's another way of phrasing that.
The magnitude of a point, I knew it will end up with a number. Same with C, right?
Mm-hmm. So that makes it possible because it is two scalars, right? Two numbers. Just replace the word scalar with number, if that helps your brain. Could you do E? A dot B and then add the vector C to your answer. Could you do that? You hit the space bar. You said something, but I didn't catch what you said.
I would believe not because the dot product would end up being a number.
Yep,
and,
scale.
And it will not have the XYZ thing.
There we go. That's the choice. So in these questions, it has a meaning or it has no meaning, and then you choose from a selection. Why? Right? Okay. And the last guy we're going to do is a total pain in the posterior. Oops. Well, I got the answers here anyway, but let me just do it as if they weren't there. I'm glad they are, because it's making my life a lot easier when I don't want to screw up. We are going to get or calculate the scalar projection of vector B onto a vector A. Now, I've got the answers here, but well, I'll just write down the formula first and talk about it, because there's two kinds of projections. There's the scalar projection of V onto A, and that one is going to be, I'm just copying this right off the bat here. That's this guy. And you get it by simply doing this formula. So it's a plug and chug. Right. And then you have this fella. And he is, well, I definitely wouldn't write it that way, but never mind, I'll do it the way they have. It's A dot B over A, which is essentially that number. The vector A over A. Okay, now the fun part. What on earth are these scalar and vector projections, right? Scalar, vector, right? This is a scalar projection because that is a number, right? Scalars are numbers. This is a vector projection because this is a vector. So I want you to imagine that we have a vector on the ground, right? Called A. Like my pen is a vector A. And then you have another vector, and we'll join them here. But you don't need to, but we'll join them here. And this is going to be my vector B. Right, so there's my A, there's my B, right? Now, I want you to imagine that floating above it, there was, get my hands out of the way, floating above it, there was a light bulb. And it would do a vertical line so that it meets A at right angles. Now, what you have got here is this point here. This fella here, this green vector from here to here, right? This guy here. This is that guy. And see the magnitude of this vector, right? How long it is this guy. So if you want to visualize what you've got. Now, I have no idea under the sun because I'm not an engineer. I don't want to ever become one. Evidently, some engineers like to know that thing. I can't think of any decent reason in the world why they want to know it. But if they want to know it,
It's to calculate force. Like, say there's an object from up there, how much force you need for it not to slide down the slope or the angle. That's the
is
best.
that why you do those things?
Yeah.
Okay, so still not interested, but at least I now know. All I really do with these questions, when I get questions like that, is I just do the math, right? I just like the math part, right? I know there are a lot of professors in this college who love the engineering behind it. Yeah. Get to Karen Hasselbach. She loves that kind of stuff, right? She thinks the application is sometimes probably more fun than the math, and I'm kind of, yeah. The most interesting parts of math for me are the parts of math that nobody's found any use for. They're just fun because they're fun, right?
Like Star Wars.
Yeah, when engineers start finding things to do with the math, I kind of go off them a little bit, you know? but that is me. So let's do a vector. Let's suppose A is the vector 1, 0, 7. And let's imagine B is the vector 3, -2, 4, right? So I'm just randomly picking two vectors. So you're asking me to find this guy and you're asking me to find this guy, right? So all I'm going to do is do this as a calculation, right? So I'm going to get the top one, which is the scalar projection, right, of B onto A. And that's going to be A dot B over that guy. That's 1 times 3 plus 0 times -2 plus 7 times 4. It's on the top. And on the bottom, it's the magnitude of this fella. So what's that? 1 squared plus nothing squared plus 7 squared. 3, nothing, 28, that's 31. 49 squared at 50. Okay, I can handle that. So if you want to know how long is that vector, that's how long it is, right? That's the scalar projection of B onto A, means how long is the shadow, right? How long is that guy? And I guess what you just said to me, because magnitude of vectors, don't they represent forces, right? The length of it. So that's basically the force acting in that direction using this guy, right? Hope I haven't killed engineers with what I just said. That's what my feeling is what that is anyway. So that's part A done. Now, if you want to do part B, which is the vector projection of A onto B, now I understand why they wrote it this way, because can't we use this answer? Because we already found it, right? A dot B over A. So I know this answer is that number times the vector A over the magnitude of A. So this mess is him, right? So I'm just using this answer, yeah. And let's see what we've got. 31 over the square root of 50 times, okay, you want to figure out what that looks like. In my brain, that's the same as that. So it's 31 over the square root of 50. 1 over the magnitude of A is 1 over the square root of 50. And then the vector A. And those two get you 50. So I have 31 50ths of that vector, which ends up being 31 50ths, 0, and 7 times that's 210, 217 50ths. And that vector is the green vector, right? Not the magnitude of it, but that's what that green vector would be, right? That's its components. How are we doing, guys? We're good. Okay, good. So let's continue with our next section because we've basically finished that one. So the next section is going to be called the cross product, and that's section 12.4. Have any of you in your engineering classes, whatever, done a cross product?
We're doing it in statics right now.
So when you did it in statics, did you do a 3x3 determinant, or did you use some really ugly formula with A1s and B2s and all sorts of things floating around? Okay, how do you do it?
For cross products, we got shown to use MATLAB for those because it's like really ugly.
Oh, you ain't getting MATLAB off me. You're getting it. You're getting it pure. Oh, don't complain. Before we get there, let me give you a little bit of background. For not everyone has done vectors, and so you can't just assume that just because half of you have, that the rest are somehow going to pick it up through osmosis. So I want you to imagine we've got two vectors in 3D space. There's U. Make this decidedly different length as well. There's V. The cross product and it's typically going to be written as U cross V. That's how you say it out loud. U cross V, right? The cross product, U cross V, is a vector that is, I'm not using the fancy word, orthogonal, right? It's at right angles to both U and V. So when you get a cross product of, say, these two vectors, that red vector would be an example of it. Can you see that it makes a right angle, right? It's orthogonal to 2. So I'll try and draw it here. This is what U cross V looks like. It has the property that it makes a right angle with U and V. U and V are probably not going to be right angled, right? That's like U and V. But won't the cross product be that? Now, don't think of the floor, because this is true even when they're bent at funny angles, right? Can you see it with, So that's what we're going to be calculating. A vector that is orthogonal to two vectors U and V, called the cross product. And they make, oh, I'll always get this one right or wrong. I think they make they're called the right hand rule. So that when you do them, your thumb points in the U cross V direction. Now, if it's not the right hand rule, they make the left hand rule, right? Because either my thumb is the right one or, oh, I think it's a left hand rule. Now I'm looking at my fingers. So it's a left hand rule, right? The thumb points in the direction that you would get those. And evidently, things like electric motors and things, this rule helps you tell which direction the magnetism or the north is pointing, or whatever that thing's called. So far, so good, right? That's just a theory. There's no calculation yet of how we get it. That's still to come. But that's what you are finding when you get a cross product. You're finding a vector that is orthogonal to U and V at the same time. And it does lots and lots of things and is useful for lots and lots of things that you wouldn't have imagined at this point in time. So now I'm going to do something before we go here, and we're going to look at what's called the determinant of a 2x2 matrix. Now, a 2x2 matrix, a matrix is just a table of numbers, right? That's a 2x2 matrix, right? It's got 2 rows and 2 columns, right? 4 numbers altogether, right? And that's a 2x2. And the determinant is a number, a single scalar, and you get it by multiplying these two guys together, and they're called the major axis. Subtract those two guys, multiply together, and that's called the minor axis. So you will hear me going major, take away minor an awful lot. So in this particular case then, major axis is 2 times 4, take away minor axis, 1 times 5, and the answer I get is 8, take away 5, and so that answer would be 3. Right, back to me asking the vector people, did you incorporate a guy that looked like that in your, no, you told me you did it all by computers. Did you ever do any of them using this?
Yes.
I use the 3x3.
Right. And ours is going to become a 3x3. But did you ever do the 2x2 as part of the 3x3? Because you need to do the 2x2 first. Okay, then this is good because this means everybody's in the same boat, right? We are going to find that this fella, right, the little 2x2s, is going to be helpful in getting the cross product. So here is our question. U is 5, 3, -1. V is -2, 1, 1, right? Two random vectors, nothing special about them. To find the cross product, first thing you're going to do is set up a 3x3 matrix. You put an I, a J, and a K as the first row. U goes next. You only put the numbers in 5, 3, -1. V goes last. You only put the numbers in -2, 1, 1. Does that look familiar to some of you? Right. Then you just follow instructions. The answer is going to have 3 numbers. So many I's. Yep. Take away, I know that's weird, but take away so many J's plus so many K's. So once I get a number here, here, and here, I'm done. Right? So many I's, take away so many J's plus so many K's. So let's show you how you get the numbers. I want the answer that goes here. Cover up the row in the column that has an I. Do you see a little baby 2x2 matrix? Find its discriminant. Major, take away minor. So what's that? 3, take away -1. Are you comfortable with that? 3, take away -1. Right. You want the middle one, the J. Can you see a 2x2 matrix? It's very visual. Major axis, 5. Take away -1 times -1 is 2, so take away 2. To get K, there we go. 5 times 1 is 5. Take away -6. So major, subtract minor. Actually, normally I do that in one go, but for this question, I've wrote down a little bit more. 3 take away -1 is 4. 5 take away 2 is 3. And then remember, this guy's still there. So -3 is what you get for the J component. And then 5 take away -6 is 5, add 6, you get 11. And this is probably the only time where IJK notation works for me, right? I can see a usage for it. But the minute I get the answer, you see I return back to the notation I prefer. Now, the cross product of these two vectors then, according to what I've just done, is this vector here. Agreed? Right. Cross product is this vector. I'm going to prove it only once because it takes too much time that this works. If this vector is what it's meant to be, shouldn't it be orthogonal to the vector u? And at the same time, shouldn't it also be orthogonal to the vector v? Great. And doesn't that mean then that the dot product of u with this and the dot product of v with this, shouldn't they both be 0? Because that's orthogonal. 0 dot product. So let's check it out. I'm going to do u dot the cross product. U is going to be 5, 3, -1. Dot product 4, -3, 11. Now, if this doesn't work, it's only because I screwed up in my calculations and nobody caught it. Right? So 5 times 4 plus 3 times -3 plus -1 times 11. And 20, take away 9, take away 11. Am I good or am I good? Well, all that proves is that this guy is orthogonal to U, but doesn't it also have to be orthogonal to V at the same time, right? I could have screwed up in that way. So let's do a check on this one. And the vector V is -2, 1, 1. And it's a dot product with the same guy as before. So -2 times 4 plus 1 times -3 plus 1 times 11. So -8, -3 plus 11. Give me a prize. You should be impressed. You know what I'm like. There's a lot of places where a plus could have turned into a minus, isn't there? Where a calculation could have been added wrong. Now, you wouldn't typically do that. If you were doing WebAssign, wouldn't you just put in the answer and it'd tell you we were right? But if you were doing like a midterm or an online exam, right, and you wanted to make sure that you got the points, couldn't you spend a couple of minutes doing the check? Because if it's not 0 and it's not 0, then you do this wrong, right? You gotta, maybe a plus. Oh, the most common mistake until you get used to it is people forget this subtraction in the middle one, right? They just go plus, 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 but it's plus the first one, minus the second one, plus the third one, right? There's a plus, minus, plus. Okay, I'm going to put, who will I put on this spot? Cam, is that pretty much the way you would have done it when you did it by hand?
Yeah, pretty much.
Is
I
there
would have
any,
done a little bit different.
what was said, Jeremy?
I would have put it the vectors on the matrix and put 2 of the lines on the other side as kept going off this outside of the matrix.
Oh, you're doing row echelon forms and stuff.
How it's called, but
Okay.
You know,
If it works, it's fine. I don't mind if you've got other techniques. So if you've found another way of doing this, because of a previous class, and you don't want to go, do it the way I've shown you, I have no problems, because aren't you going to get the right answer as long as you do whatever it is right? So you're good.
I like your method better.
Have you seen another method, or you just like this one because it's the first one and it seems okay?
I've done other methods before, but I like this one. It's shorter.
Okay. Well, yeah, it's very visual. If you're a kind of visual person, it's all about covering things up in major, takeaway, minor, which is my kind of brain. So I'm happy with that type of way of doing it. But there is a formula right there if you want to go find it. It's horrendously ugly, but you could do it, right? So let me give you some theory behind cross products for a little while.
My physics professor said that it was too complicated for him to explain, so he just showed us from MATLAB.
Well, now, Lewis, you've got an edge on some of the guys, don't you?
Yeah.
Yeah. You could make money by selling the idea to some of them, saying, I got another way of doing it, but it'll cost you. You thought about that?
Yeah. Do it all the time at work when somebody has to charge them $1.
Okay. Oh God, if I had to do that, I'd be poor by now. So I'm glad I don't charge $1 a time. Right. I'm making this up, but well, actually, I'll not make it up because I do have some numbers. Right. This guy that we just did a minute ago ended up being that vector. You might think that if you do a cross product and you just switch places, that you get the same answer, right? But you don't. But you do get a similar answer. Anybody tell me what the similar answer would be?
negative prefers.
It's the negative of this guy. So basically just change everybody's sign. Now, since I've decided that this guy is a right hand, when you do this guy, it's a left hand. One, if you draw the picture of what it might look like, right? If this is U and this is V, the cross product that we just got is that one. If you switch places, the cross product you get is this one. Do you see it's parallel to it, isn't it? Just one points up the way and the other points down the way, right? One, your thumb points up the way and the other, your thumb points down the way, right? That's really the only difference. So far, so good?
So is that relative to the x-axis when you're switching the, you go in reverse?
No, that looks vertical, but in real life, these vectors are pointing at weird angles anyway. Right, so u cross v would be this and v cross u would be that side. So the x-axis is not any significance. Now,
But wouldn't it be reversed to all the numbers though?
I hope I did reverse all of them. Did I? No, I didn't, did I? There we go. Now I've done it. Suppose I did a cross product, could happen, and I get the 0 vector as my answer, right? Still a vector, but it's that vector. Ooh. What is the geometric interpretation of what the heck is going on? What's the only way that could happen? And we'll assume that u and v aren't the 0 vector because that's a trivial situation, right? How could two non-zero vectors still get your cross product of 0? What are you looking at when that happens?
They're in line with each other,
Yeah.
facing each other.
Yeah, the jargon for that, what you just said, makes sense. They're parallel vectors. Right? They look like that. Or side by side, right? And nobody cares about length, right? So one of them could be twice as big as the other. It wouldn't stop the answer being the 0 vector. And doesn't that mean then that you can have a quick test on are two vectors parallel? Well, maybe not a quick test, but at least a test. Can you do the cross product? And if it's 0, 0, 0, you can now say these two vectors are parallel, even although the numbers could be extremely big or, you know, -7/11 and 3/9, and, you know, values that you would find very hard to tell if the two vectors were parallel or not. Cross product. Now, there is a guy called a triple product. And I'm going to change the letters to A dot B cross C. Right, here's my first question. Is the triple product a scalar or a vector? In other words, is it a number or is that a vector when you're finished? What is A dot B cross C? Scalar, a number,
Scalar.
or a vector?
It is a
I was-
vector.
You think? Okay. Well, let's talk it through. Would you agree that B cross C is a vector? Right. And A dot a vector. What does A dot another vector get you? What does a dot product always get you?
Vector.
Dot products always get you
A scalar.
a scalar. So that's called a triple product because it's got, I guess, 3 things in it, right? 3 vectors. A dot B cross C. Right. Now, here is some interesting property. Sometimes, most of the time it's not true, but sometimes it's 0. Sometimes the triple product is the number 0. And not the 0 vector, but the number 0. Anybody got any ideas what that is telling me about the 3 vectors A, B, and C? Because it is telling me something quite interesting. Last chance. Any thoughts on what it might be telling you? Here goes. all three vectors are on the same plane. That means they all fit on a piece of paper, right? It doesn't need to be horizontal, right? It could be, you know, an angle. And when that happens, we say that they are coplanar. So if the triple product is 0, right, the number 0, you have now got proof that three vectors are coplanar. So if you didn't have this test, wouldn't it be very difficult to tell just by looking at three vectors? You know, that's what not coplanar looks like. Can you see the three vectors are pointing every which way? What does coplanar looks like? Do you see that they all fit on the Hammond, you know, flat piece of paper, right? That's what coplanar looks like. That's what not coplanar looks like, right? Coplanar? Not coplanar. If you want to test for that, you find the triple product. Do you think it matters which one you do first, second, or third? Could I do B dot A cross C? Do you think that would matter? Nah, don't matter. Because since the answer is 0, sticking a negative in front of it, it's not going to make it less 0. Agreed? Because that's about the only thing that could go wrong with that. I'm giving you a whole load of the theory to finish off today, because when I see you tomorrow, we're going to be calculating these various guys and using them. So I want you to imagine I've got a vector A, I've got a second vector here, B, and I've got a third vector, which is not coplanar or orthogonal or anything else. It's right, 2, 3 boring vectors, right, that have none to do with each other, right? They're all pointing any which way but loose. Right. Now, if you find the triple product, you will not get 0, right? If they're not coplanar, you'll get a number. And let's pretend that this number is 42. And you're trying to think, what is the number 42? What is it that I've just calculated? Well, if you can imagine another vector, same length as A, another vector here, same length as B, and then a vector C going like that, and a vector C going like that, and another vector C going like that, and then you join everybody together. Do you see what you make is a 3D solid, a 3-dimensional solid? Now, it might look like a cuboid, right? A box with corners in it, but none of these angles are right angled, even if they look like it. It's more like a box that somebody sat on, right, and bent it a lot, right? That shape, not kidding, I love this name. Right, this solid shape is called a parallelogram. Come on, is that not a cool? Rolls off the tongue. It's called a parallelepiped. 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 And we have just found its volume. Is that not cool? The
Who's it named
triple.
after?
I don't think it's named after a person. I think parallel is because it's parallel. I'm not sure. The epiped is probably Greek or Latin, right? Is that not a cool little interesting property of what a cross product, along with a dot product in this case, generates, right? It gets you the volume of that funny shape. Let's do a not two-dimensional, a two-vector situation. Let's call this guy A, right? Call this vector B. I know what A cross B is, but I'm not going to do that. I'm going to find the magnitude of A cross B. Now that's the magnitude of this vector. And that, let's pretend that's 42, right? And you might be saying, what is the number 42 then? Well, if you draw another vector parallel this way and another vector parallel that way, can you see that you're always going to get a parallelogram? Great. As long as these are not
Is that the
collinear.
perimeter or the area of that
It is,
shape?
in fact, you were on the right tracks. It's actually the area. So if you want to know the area of a parallelogram, right, that's a 2D shape, in 3D space, because couldn't these two vectors be slope them upwards, right? Imagine the other two going like this and this. You want to find the area of that shape, just find the magnitude of its cross product. And if you think about it, there's no reason in the world why the length of this blue pen, which is roughly what the cross product looks like, why the length of that vector, right, should be the area of A and B. Would you agree it doesn't, intuitively, I can't see the connection, right? But nonetheless, that's what it is. Would you agree that this triple product, being the volume of this parallelepiped, intuitively doesn't seem like there's a reason why that should be true, but nonetheless it is. Suppose I wanted to find the area of a triangle where A and B in 3D space, right? So there's my A going this way and there's my B going that way. And I want the area of this triangle. I know the magnitude of the cross product is the area of the parallelogram. How could I use this to get the area of just the triangle?
Divide by 2.
Right. Another way of saying that is it's a half. Do you see this cross product is getting used in all sorts of ways that have got nothing to do with finding the vector that's orthogonal to A and B? You see that? It's giving you areas of triangles. It's giving you areas of parallelograms. It's giving you the volume of a 3D shape called a parallelepiped. Well, as long as you stick a dot product in front of it. Isn't it also telling you if two vectors are coplanar, right? Or I should say, this guy is telling you if they're coplanar, right? A, B, and C are coplanar. Come on, you should be impressed by this. This is cool stuff.
Could you also use it to find the area of a pyramid?
Oh, a 3D thing? Ooh, I don't know. I'm trying to think. Don't quote me on this because I'm probably wrong. But if the pyramid has this guy as a base, this is probably a third of its volume. I'm just thinking out the box here.
Yeah,
Don't
sounds
quote
right.
me on this because I could be wrong, right?
Yeah,
It does all sorts of things.
it's pretty cool.
Right. So we should finish with a joke. I try.